Hi, I'm Ben-Yaakov. The title of this presentation is the Zeta converter made simple and how did it evolve. The Zeta converter consists of a switch, two inductors, a series capacitor, and a rectifying diode. The switch is turned on and off in a certain duty cycle and delivering power from the input to the load, which is described here as a load resistor as well as a filter capacitor. Now the analysis that I'm going to present here relies on the following assumption: that the ripple is small and that the diode voltage is low and can be neglected, although I'll mention when it can be or when should it be taken into account. The resistances are low, and finally that the operation is in the continuous conduction mode, namely that the current of the inductor never comes to zero, but rather the inductors have currents of this shape, that is, it does not go to zero. This will be an inductor current. This converter is called dual SAPIC or Zeta. Before starting with the analysis, I'd like to make a point regarding an inductor and the average voltage across it. It is important to understand this concept because it simplifies very much the analysis. Now, if we have an inductor, we can say that the average voltage on the inductor must be zero because the state space equation of an inductor is V equal to L di over dt, that is L times the rate of rise of the current, or you can say that the average voltage is L di average over dt. Now, if we assume steady state, that the inductor current doesn't go up or down, but rather stays in a constant average value, this would mean that the IDT average is zero, which then implies that the average voltage is zero. Normally, you'll find across an inductor a positive voltage and then a negative voltage. This would be an inductor voltage as a function of time. Now, if we say that the average voltage is zero, this would imply that the area here, let's call it A1, is equal to this area A2, so the average is zero. With this, let us continue with the analysis of the Zeta converter, and the key information that we really need for the analysis is what is the voltage or the average voltage on the capacitor. Now this is now very easy to find out because looking at L1, average voltage is zero. Here we have zero voltage. Consequently, the average voltage here at this point that I'll call Vx must be zero. Now I move here to the next point, call it Vy. Again, L2 has an average voltage zero. We have here V out, so consequently Vy average is V out. So we find that the capacitor is charged to V out with the polarity that I've just indicated. So this is really simple. Let's move now to the actual analysis of the Zeta converter, and let's have a look at the inductor L1 and see the voltages as a function of time that we are going to find out during the on time and the off time. On time and off time refers to the switch. Now during the on time, the switch is on. This point is equal to V in, so we're going to find on L1, I'll call this like the positive side of the inductor, we'll find here a voltage which is V in. This is during T on. Now during T off, the current through L2 will be passing through diode D. Therefore, this point will be practically zero. Vy at this particular minute will be almost zero. Of course, there is a voltage drop on the diode, and if the output voltage is low, then one might wish to take this voltage drop into account. We are going to neglect it in this analysis. So if Vy is indeed zero, and the capacitor voltage is plus minus V out, it implies that the voltage at Vx at this time of T off will be V out. So during T off, we're going to have minus V out actually. Now, since this area must be equal to this area, then V in times T on is V out times T off, dividing by the period T, which is this time here. We have V in times D on equal to V out times D off, from which we get that V out over V in, which is the voltage gain of this circuit, is D on over D off. Now this implies two things. Number one, that the output is the same polarity as the input, and secondly, that the gain could be higher and lower than 1. When D on is 0.5 and D off is 0.5, then the gain will be 1. Now for D on larger than 0.5, we'll have a gain larger than 1, and for D on smaller than 0.5, we're going to have a gain lower than 1. Now, what about L2? Well, the situation here is pretty much the same. During the on time, this is when the switch is on, we have here V in. We have, however, the capacitor being charged in this polarity to V out. So if we look at the voltage across the capacitor, we see V out here, and we see here on the other side V out plus V in. When we subtract one from the other to get the difference, we are getting again V in. So during T on, we'll get V in. So during T off, the current is going this way. This point is approximately 0, and therefore the voltage across L2 will be minus V out as we had it before. So obviously we can calculate from here also the ratio of V out to V in to be D on over D off. Summarizing now the characteristic of the SEPI converter, which is the precursor of the dual SEPI. As you can see, it's very similar, except that it has a inductor in series here and an inductor in parallel here, while in the Zeta it's reversed. This is why the Zeta is called the dual SEPI. Now for the SEPI, we have an up-down, we have non-inverting, we have a series capacitor, which could be useful to protect against shorts at the output. There are two inductors, but we have a pulsating output current in the SEPI. On the other hand, in the dual SEPI, or Zeta that we have just discussed, since the inductor here is in series with the output, while here the parallel inductor is in the input, we are going to have the same characteristic. It's up-down, non-inverting, series capacitor, two inductors, but now the pulsating current is at the input and not at the output. Now, a few words about the evolution of this topology. The first time that this topology has been described in literature in a publication, and this was in 1981 in the IEEE Transaction on Industrial Electronics. It's a paper by Josvik and Kazimierczuk, dual SAPIC PWM switching mode DC to DC power converter. So they called this circuit, which we have analyzed, the dual SAPIC, because it's like the SAPIC, except the reverse placement of the inductors. The first time, to my knowledge, that this circuit was called Zeta is in this paper by Perez, Martins, and Barbie, and it was published in 1994. And they actually seem to have coined the name Zeta because this dual SAPIC, or Zeta, is the sixth in the sequence of basic PWM converters, the buck boost, chuck, SAPIC, and the dual SAPIC, which they have called Zeta, which is the sixth Greek letter. So this is apparently how this name evolved. This brings me to the end of this presentation. I hope you enjoyed it and you'll find it useful. Thank you very much for your attention.